In the last class, we have learnt about uh, root 2 as an irrational number. So prove that root 2 is an irrational number. In this class, we are going to do exercise 1.3. So before going to do that, we recall that how we have proved root 2 is an irrational number. Okay, now let us take another example. 5 minus root 3 is an irrational number. So we need to prove that 5 minus 3 is an irrational number. Okay, so let us assume 5 minus root 3 is a rational number. So first we have to assume that 5 minus root 3 is a rational number. So after assuming that, so you know that a rational number can be written in the form of p by q or a by b. So a and b are integers, a and b are co-primes. So co-primes, we have explained that what is co-prime. Co-prime is a number which have a common factor 1, and other than 1. See, look at here, 5 and 3 are co-prime because it has common factor 1. 10 and 15 is not co-prime because it has a common factor 5. See, if anything has a common factor 1 is called co-prime. Okay, after that, so keep root 3 here and transpose 5 to that side and right hand side, you will get minus 5. Look at a by b minus 5. So all are integers and rational number. So this can be written as a minus 5b divided by b. Okay, so take LCM here, b 5b, a minus 5b divided by 5. Okay, after that, since a and b are integers, so you can write like this. Since a and b are integers, so we can say that this is rational. Okay, so this becomes rational. A by b minus 5 becomes rational. So here root 3 is an irrational, but a by b minus 5 is rational. So this contradicts the fact that root 3 is irrational. Okay, so contradiction arises because our incorrect assumption that 5 minus root 3 is a rational, that we can conclude that 5 minus root 3 is irrational number. Okay, this is how we are going to prove. Okay, now we'll see the exercise 1.3 first problem. Exercise 1.3 first problem. Prove that root 5 is irrational. Prove that root 5 is irrational. Okay, the first step is, let us assume that root 5 is rational number. So you need to assume that root 5 is rational number. So if that is a rational number, root 5 is equal to a by b. We can express it in the form of p by q or a by b. Okay, so root 5 is equal to a by b, where a and b are co-primes. Already explained in the previous problem what are co-primes. Okay, so a and b are co-primes, means it has a common factor only 1 has common factor. Now rearrange this, so you just write like this: b root 5 is equal to a. So I got the value of a is equal to b root 5. So equation number 1. After that, squaring both sides. So we need to square both sides. So after squaring this, a square b root 5 whole square. So here square and root will get cancelled. Square and root will get cancelled. B square into 5 is equal to a square. Now you can see here b square can be written as a square by 5. This means 5 divides a square. This means 5 divides a square. Look at here, 5 divides a square and also divide a. 5 divide a square and also divide a. So we can write, take another number a as 5c, because here already 5 divides a square and a. We can take any other integer, 5 multiples of 5, that is other integer c. Okay, so this is equation number 2. Look at equation number 1, a is equal to b root 5, and equation number 2, a is equal to 5c. Now we can equal 1 and 2. We can equal equation number 1 and 2. So then it becomes b root 5 is equal to 5c. Okay, so again we'll square on both sides. So b root 5 whole square 5c whole square. Now square and root will get cancelled. B square 5 is equal to 5 5 is a 25 c square. Okay, now b square is equal to 25 5 times you can divide 25 5 times and then c square. Now b square is equal to 5c square. Look at that, b square is equal to 5c square. 5 divide b square and also 5 divides b. So here a and b have common factor 5. A and B have a common factor 5. Initially what we have assumed that they are co-primes. They have common factor only 1. But here, so we have proved that A and B has a common factor 5. This contradicts the fact that A and B have no common factor other than 1. So this contradiction arises because our assumption root 5 is a assumption. Okay, so now therefore root 5 is irrational number. Okay, so next, second question. We'll go to second question. Prove that 3 plus 2 root 5 is an irrational number. Prove that 3 plus 2 root 5 is a irrational number. The same thing we'll do. Let us assume that contrary, that 3 plus 2 root 5 is rational. So first we have to assume that that is rational. Look at here. So when we consider this is rational, we can express in the form of p by q. Okay, so this is equal to a by b. So a by b, a and b are co-primes. Okay, a and b are co-primes. Now what I do is I'll transpose this 3 to right hand side. 2 root 5 is equal to a by b minus 3. Okay, now this will take LCM now. 2 root 5 is equal to a minus 3b divided by b. Okay, after taking LCM, now I'll send this 2 to down here, divide by 2. So root 5 becomes a minus 3b by 2b. Again, if I divide this 2b, a by 2b, and I'll split minus 3b by 2b. bb gets cancelled here, bb gets cancelled. Now we got a by 2b minus 3 by 2. So this all become a rational number and integers, rational number and integers. So it is a rational, and so root 5 is a rational. So root 5 is a rational, but this contradicts the fact root 5 is irrational. This contradiction is arises because assumption of 3 plus 2 root 5 is rational. Okay, so therefore 3 plus 2 root 5 is an irrational number. Okay, this is the second question. Now we'll go to third question. So what is the third question now? Here, so we need to prove that. So 1 by root 2, 7 root 5, 6 plus root 2 is irrational number. Okay, so first we'll take 1 by root 2. The first step is, let us assume that 1 by root 2 is a irrational, first rational number. So as usually see, 1 by root 2 is equal to a by b. Okay, so a and b are co-primes. So b is equal to root 2a. So we will cross multiply. You cross multiply here and you will get c. B will go to here and root 2 will go here. B is equal to root 2a. Squaring on both sides, you can get b square is equal to 2 into a square. That means 2 divides b square and also divides b. So that a and b has a common factor 2. This contradicts the fact that a and b have no common factors other than 1. The contradiction has arisen because of our assumption is root 2 is rational. So that's why it is a irrational number. Got it? Okay. Next, second question. So what is the second question? 7 root 5. 7 root 5. Let us assume that 7 root 5 is a rational number. Let us assume that 7 root 5 is a rational number. So as usual, you are writing 7 root 5 is equal to a by b. Okay, so the same thing where a and b are co-primes. Now what I do is I'll take this 7 to denominator. So root 5 is equal to a by 7b. So see here, a, 7, b are integers. All are integers. So rational number. So a divided by 7b is a rational number. So root 5 is rational. This can't contradict. Root 5 is a irrational. So we can conclude that 7 root 5 is a irrational number. Got it? So this is the second problem or third question. Now we'll go to the third problem. 6 plus root 2. Let us assume that 6 plus root 2 is a rational. So let us assume that 6 plus root 2 is rational. 6 plus root 2 can be written as a by b. So 6 plus root 2 is equal to a by b. We know that a and b are co-primes. A and b are co-primes. A and b have no common factor other than 1. So we assume this. So therefore root 2 is equal to a by b minus 6. Look at this. I can take this 6, transpose this 6 to right hand side. So you will get this. Since a and b are integers, is also rational. So that root 2 is a rational. So this contradicts the fact that 6 plus root 2 is a rational. So therefore 6 plus 2 is a irrational number. Got it? So children, you understood how to prove that given a irrational number, we can prove by contradiction. So this is called proof by contradiction. Okay, so these are the numbers. Now we'll go to the next concept, is important theorems on expansion of rational number. Important theorems on expansion of rational. The first theorem says like this: let x be rational number whose decimal expansion terminates, then it can be expressed in the form of p by q, where p and q are co-primes. Okay, and the factorization of q is of the form of 2 to the power of n and 5 to the power of m. So where m and n are non-negative integers. Okay, so this is the theorem. Now I'll explain how it is, giving an example. 3 by 8. Now look at this example, 3 by 8. Now what is in the form? It is in the form of q by p by q. Okay, now we should not touch p here. We will take cube. So 8 can be written as 2 cube. 8 can be written as 2 into 2 into 2. Okay, 8 can be written as 2 cube. Okay, so here, according to the theorem, how it could be expressed: denominator 2 to the power of n and 5 to the power of n. So what I do is, here 2 to the power of 3. Now I'll multiply both numerator and denominator by 5 cube, because here exponent is 3. Here also exponent should be 3. So 5 to the power of 3 divided by 5 to the power of 3, both the side I'll multiply, and then this become 375. How you get 375? 5 cube means 125 into 3 is 375, divided by, look at here, 2 into 5, 10. 10 cube. 2 into 5, 10. 10 cube. How did you get this? So you can write like this: 5 whole bracket is cube. Now this become 10 cube. Now 10 cube means 1000. What is 10 cube? Is 1000. So 375 divided by 1000 means 0.375. 0.375. So this is how you can write the decimal expansion. So let us consider another example. 7 by 80. So 7 by 80 can be written as, look at this, 2 to the power of 4 means 16. 16 5s are 80. So look at this, how we can write. So here 2 to the power of 4 and 5 to the power of 1. So instead of writing, so what you have to do is, it should be same power. Okay, look at here, 7 into 5 to the power of 3, 2 to the power of 4 into 5 to the power of 4, because here already 1 5 is there, and you have another, so multiplying 5 to the power of 3 on both sides, numerator and denominator, you will get 875. You will get 875, and denominator you will get 10 to the power of 4. This can be written as 0.0875. Now, from these two examples, what you have understood is denominator p by q. If we take the q, if it is rational number, expansion is stopped, means terminated, means here, so it could be expressed in the form of 2 to the power of m, 5 to the power of m. So only 2 to the power of n and 5 to the power of m. So here also you can see 2 to the power of n and 5 to the power of m. So this is if this is the case, then it is terminated. Decimal is going to be terminated. Okay, next theorem, what it says, let x be p by q. It's a converse theorem. P by q, rational number, such that the prime factorization of q of the form of, now it is in the form of 2 to the power of n, 5 to the power of m, then m and n are non-integers, non-negative integers, then has a decimal expansion which terminates. So decimal, now we have to find out whether it is terminating or non-terminating or non-recurring, recurring, all these things. So it's very difficult, no? So from this theorem, we can easily find out that whether the decimal expansion is going to be terminate or not. Okay, so this theorem says, and this is a converse theorem. So another theorem we can say that, let us take x p by q is a rational number that prime factorization is not of the form. So look at here in this theorem what they are saying. So prime factorization is not in the form of 2 to the power of n, 5 to the power of m. So where m and n non-integers, non-negative integers, then the decimal operation expansion which is non-terminating and non-repeating. Okay, so here what we have understood means, if the decimal expansion is terminating, it would be in the form of, denominator should be in the form of 2 to the power of n and 2 to the 5 to the power of n. So suppose if we are understanding that 2 to the power any denominator q, 2 to the power of n and 5 to the power of m, if it is in the form of that, then this decimal will be terminating. So that is the converse of theorem. If the decimal is non-terminating and repeating, then the denominator, it is in the not in the form of 2 to the power of n and 5 to the power of m. Okay, so this is what the theorem says. So by this theorem we will do the exercise 1.4. okay, read the exercise 1.4. The first question in the exercise 1.4, without actually performing the long division, state whether the following rational numbers will have terminating decimal expansion or non-terminating repeating decimal expansion. Now we are using, you have to use this theorem what we have done. Okay, so actually without actually dividing it. Okay, so we have to say that whether it is terminating decimal or non-terminating repeating decimal expansion. Okay, so let us consider first example, first problem, 13 divided by 3125. Now this is how that it is in the form of p by q. It is in the form of, this is rational number, right? This is in the form of p by q. Now let us take the prime factors of q. We should take the prime factors of q. So 3125, 5 is a 225, 5 is a 125, 5 is a 25, 5 is a 5. How many 5s are here? 5 to the power of 5. We can write like this, 5 into 5 into 5 into 5 into 5. See how many 5s are? 5 to the power of 5. So this can be written as like this. Okay, 3125. Okay, so now how we can write in the form of, now we should write in the form of 2 to the power of n, 5 to the power of m, right? So let us see. 13 divided by 3125 is equal to 13 divided by 5 to the power of 5. This is a terminating decimal expansion. This is in the terminated decimal expansion, because here you can see, so if 5 to the power of 5 to the power of m, it is in the form of 5 to the power. We can also write 2 to the, there is no factor, prime factor 2, we can write 2 to the power of 0. Okay, then we can write 2 to the power of 0 means 1, right? Anything to the power of 0 is 1. So you already know that from the law of exponents. So we can write like this. So if this is the case, we can express in the form, this form, right? So this is terminating decimal expansion. Got it? Okay. So we'll go to second problem. The second problem, 17 divided by 8. Okay. You know that 8 can be written as 2 to the power of 3. Okay. Here also you can write what? So into 5 to the power of 0. Okay, you got it. So no problem. 5 to the power of 0 means 1. So we can express in the form of 2 to the power m into 5 to the power of m. So this is also terminating expansion, decimal expansion. Got it? This is also terminating decimal expansion. Now consider 64 divided by 455. Here we'll write this 5 sevens are 91. So 13 sevens are 91. So 13. 5, 7 and 13. See, 5, 7 and 13. Now let us write this. 60 divided by 5, 7, 13. This is non-terminating and repeating. Why? Because here the numbers are 5. 5 to the power of 1 we can take. So here 7 and 13. So the prime number 7 and 13 are different number. So it is not in the form of 2 to the power of n, 5 to the power of m. So that's why this is non-terminating and repeating. Got it? Whereas in these two problems, we could write these numbers in this form, right? So 2 to the power of n into 5 to the power of m. But here we cannot write this as 2 to the power of n into 5 to the power of n. That's why this is non-terminating and repeating. Got it? Okay, next we'll take 15 divided by 1600. 15 divided by 1600. Let us see the prime factors of 1600. 1600, 2 800, 2 400, 2 200, 200, 250. So again from 5, 525, 5 ones are 5. So these are the prime factors of 1600. Now let us write this prime factor. How many 2's? 1, 2, 3, 4, 5, 6. So 2 to the power of 6 into how many 2 5's? 2 5's. So 5 to the power of 2. Okay, now see, we can write this is in the form of, look at this, 15 divided by 2 to the power of n into 5 to the power of m. So we can write, okay, that's why this is decimal expansion is terminating. Okay, it is terminating decimal expansion, because we can write this denominator as 2 to the power of n into 5 to the power of m. Okay, so let us go to the next problem, fifth problem. 29 divided by 343. 29 divided by 343. So 29 will write as it is. So 343 means 7 cube. 7 cube is 700. So here no 2, no 5. Denominator no 2. That's why non-repeat, non-terminating and repeating decimal. Okay. Now we'll come to the next one. 23 divided by 2 to the power of 3 into 5. And already it's given. It's in the form. That's why terminating and terminating it, because it is 2 to the power of n into 5 to the power of m. So again you can see here 129 divided by 2 to the power of 2, 5 to the power of 7, 7 to the power of 5. Okay, here one extra, that is 7 to the power of 5. It should not have been present here. So it is present means this is non-terminating and non-terminating and repeating decimal, because if 2 to the power of 2, 5 to the power of 7 is there, then we could have written this terminated. But there is a 7 to the power of 5 is there. That's why it is non-terminating and repeating decimal. So it is non-terminating. It's in the form of 2 to the power of n, 5 to the power of m. Let me take this 6 by 15. 6 by 15, 2, 3 is a 3 is a. So have a common factor 3, 3. Look at here 3, here also 3. So take 3 as a common factor and you will get this terminating, because there is no 5 and 2. So there is no 5 and 2. So that's why it is terminating. So 5 and 2 is there. Okay, we can write. So 2 to the power of 0. So that's why it is terminating. So here also you can see 5 and 2. So this is also terminating. Here 2, 3, 5. So 1, 3 extra is there here. So you can see that's why it is not terminating. So you understood. So how terminated the decimal expansion terminates and non-terminating and repeating. So this is how we can find out the problem. Okay, next, second problem. Write down the decimal expansion of these rational numbers in the question 1 which have terminating decimal. Now we need to write the decimal expansion, how it would be. So we got it 13 by 3125 as a decimal expansion. How you write? So 13 by 5 to the power of 5 we can write as, we will multiply 2 to the power of into 2 to the power of. Why we are going to multiply 2 to the power of 5? So in the denominator you see, so 5 to the power of 5 can be written as 2 to the power of 5. Then when you multiply 5 into 2, what will get? 10. So 10 to the power of 5. So multiply these two, you will get 10 to the power of 5. So that's why you're going to multiply with 2 to the power of 5. So here 13 into 32, 2 into 2 into 2 into 2 into 2, that is 32, divided by 10 to the power of means 1 followed by 50, 1 followed by 50. Okay, so 416, 1 followed by 50, this can be written as 0.00416. So this is terminating decimal. Let me take 17 by 18. 17 by 18 here. So anyways we need to take this 2 into 5 whole cube. So 2 into 5 whole cube means 10 cubes. So here 17, 5 into 5 into 5 means 125. So when you do it, 2125 divided by 10 cube means 1 followed by 30. Okay, so this can be written as 2.125. Next we'll take 15 by 1600. So this can be written as 3 divided by 320. So here 15 divided by 5 to the power of 2, 2 to the power of 6. Multiply with 5 to the power of 4. So because we need to we should get equal okay, you should get equal power. That's why you should multiply 5 to the power of 4. So when you multiply the 5 to the power of 4 with 15, you will get 9375 divided by 2 to the power of 6 already is there, 5 to the power of 7. 5 to the power of 4 into 5 to the power of 2 is equal to 5 to the power of 6. This can be written as 0.0009375, because here 2 into 5 wholes to the power of 6 means 10 to the power of 6. So multiply 10 to the power, divide by 10 to the power of 6, you will get 0.009375. So that is the expansion. Now here in this you can easily write that 23 divided by 2 cube means 8, 5 square means 25. So multiply 25 into 8 means 200, 23 by 200. So this can also be written as okay, how we can write, you see. So 115, 10 cube, that is 0.115. So this is easy, 0.4 and also 0.7. Got it. So this is how we can write in the decimal expansion. Now let us take third question. The following real numbers have a decimal expansion as given. In case decide whether they are rational or not. If they are not rational, if they are rational and of the form of p by q, what can you say about the prime factors of q? Now they are telling that we need to find the prime factors of q. First number we'll take. So 43.123456789. This can be written 43. 1 2 3 4 5 6 7 8 9 divided by 1 followed by 9 zeros, 1 followed by 9 0. This can also be written as 4 3 4 3 1 2 3 4 5 6 7 8 9 divided by 1 followed by 9 zeros. Okay, this can also be written as, so 10 to the power of 9. 10 to the power of 9 can also be written as 2 into 5. 2 into 5. So look at here how we can write 10. We can write 2 into 5, right? So then to the power of 9, it can be splitted. 2 to the power of 9 into 5 to the power of 9. So then this become 2 to the power of 9 into 4. So this is in the form of theorem, 2 to the power of n, 5 to the power of n. So rational number. So this is rational number because it's in the form of 2 to the power of n, 5 to the power of n. Okay, second question. So 0 0.120 1200 Look at this is an irrational number. We can easily say that it has got some pattern. That's why it is irrational number. So therefore, directly we can say that it cannot be expressed in the form of 2 to the power of n and 5 to the power of m. Okay, next number is 43.123456789 repeated because bar is given repeated. This is also rational number, we know that, but for a convenience, see here 43 1 2 3 4 5 6 7 8 9 divided by 1 followed by how many zeros? 9 0 because 9 digits are. So denominator contains a factor 2 and 5. Okay, you can express now. So to the power of 9, here we have expressed 2 to the power of 9 into 5 to the power of 5. You can express this. So this is also rational because 2 to the power of 5 and 5 to the power of 6 and 17. This is 17. So multiplied by 17. So this is there we end the chapter a real number. So exercise 1.4, exercise 1.3, and thank you children.